We will start with problem statement. Firstly, we have to find or create a transfer function with at least one k value, 2 poles and 3 zeros, as the example shown below. Secondly, based on the above transfer function, we have to use Scilab and bot plot technique to illustrate its amplitude response and phase response. We have to show the gain crossover frequency, phase crossover frequency, gain margin, and phase margin for the transfer function. Next is we have to use lead and lag compensator to further improve 10% of the current phase margin of the response. We also have to show the final transfer function of the compensator and its phase and also amplitude response. And lastly, based on the lag and lead compensator, we have to choose which compensator that can use to achieve 10% improvement.
My name is NADIAH. Now we will go to the objective of this project. So first is to determine the gain and phase margin of the transfer function. Second is to further improve 10% of current phase margin of the response by using lag and lead compensators. Third is to determine which compensators that can be used to achieve 10% improvement of phase margin. So for the methodology part, this is the manual calculation to find transfer function of the system. We can find the amplitude plot and the phase plot. From the transfer function, we can find the resultant slope for log amplitude plot. Then we will find the resultant slope for phase plot. Then this is the dot plot for the transfer function in the Scilab. As we can see, the system is unstable because K margin at right below and the phase margin at left above. From the Scilab, we finally obtain the phase margin, gain crossover frequency, gain margin, and phase crossover frequency. We get phase margin is 101.916, gain crossover frequency 0.852 Hz or 5.35 radian per second.
This is the calculation for phase lead. Firstly, we find the value of Vmax. The formula to find the value of Vmax equal to PM required minus PM current plus 15 degree. As the question asks us to times with 10%, we times the PM required, which is 101.92 with 10%, and our final value for Vmax is equal to 25.19. We also can find the value of alpha by using the value of Vmax. Therefore, the value of our alpha is equal to 2.484. Next, the value of our omega m is equal to 535. From the value, we can get the value of tau. The value of tau is equal to 0.119. And finally, the new value of our transfer function is equal to 1 plus 0.296s over 1 plus 0.119s. By using Scilab, we can get the value of our phase margin. Before we multiply our transfer function with the new transfer function, we can get the value of phase margin is equal to 101.91616, and our gain crossover frequency equal to 0.85. And after we multiply the initial transfer function with the new transfer function, we get the new value of phase margin is equal to 48.898, and the gain crossover frequency is equal to 3.278. This is the board plot for 10% lead. As you can see, the system is unstable because the magnitude is right below, and the phase is left above.
In this part, I will show you the calculation for phase lag compensator. Firstly, our current phase margin is 101.92, but we need a minimum at least 112.11 degree phase margin. Taking into 5 degree safety margin, we need to design a 117.11 degree phase lag network. By using Skylab, our new gain crossover frequency is 0.5622 Hz or equal to 3.532 radian. Next, we need to find gain at new gain crossover frequency. Therefore, our new gain at DCF is 2.299 dB. Then, we will put 0 1 decade below where Z is equal to 1 over tau. Then, we will find the value of tau. From here, the value of Z is 0.3532 and the value of tau is 2.831. Then we will rewrite the phase lag network transfer function as stated that. And by using Skylab, the overall phase margin is equal to 116.90 degree, which is satisfy the requirement in the question 4. So in this slide is show the graph for the bot plot after 10% lag. As a conclusion, lag can achieve a 10% improvement of phase margin because the value of phase margin increased for almost 10%, which is from 101.916 to 116.903. A higher phase margin provides a stable system. Mistake can happen when the data, including the alpha and tau, gets rounded to inaccurate decimal. This error may lead to an offset in timing, which does not offer a minimum of 10% enhancement. Through the use of Skylab software, a board diagram can be constructed for obtaining the amount of gain and phase margin. In conclusion, the system is steady since all the criteria are fulfilled to maintain its stability.